The flow of a fluid in an eccentric annulus can be visualized as the flow through a series of parallel pipes of varying diameters, the larger pipes representing the wide side of the annulus, the smaller ones the narrow side. For simplification, we will consider only two pipes of different diameters as shown on the schematic. When starting fluid movement at a low flow rate, the fluid preferably follows the path of least resistance and therefore flows faster in the larger pipe, as shown by the moving lines. Flow is laminar in both pipes. Note that the lines are representing average flow velocity and not the true velocity profile of laminar flow across the pipe section. When increasing the flow rate, the critical Reynolds number will be exceeded first in the large pipe, resulting, due to the velocity differential in the two pipes, in a combined flow regime, turbulent in the large pipe as shown by the bubbles, and laminar in the small one as shown by the lines. Increasing the rate again will eventually produce turbulence in the small pipe as well. If the fluid in the annulus exhibits a yield stress, as most drilling muds do for example, the problem becomes slightly more complex. At low flow rates, flow takes place in the larger pipe only, due to the fact that in the smaller pipe, the wall shear stress is lower than the fluid yield stress, preventing fluid movement. By increasing the flow rate, the wall shear stress in the pipe increases until it finally exceeds the yield stress of the fluid in the smaller pipe, and laminar flow occurs in both pipes. Increasing the flow rate will lead to turbulent flow in the large pipe first, and finally to turbulent flow in the smaller one as well. Note that the average velocity is always higher in the large pipe than in the small one, whatever the flow regimes present. However, the ratio of the average velocities between the two pipes in turbulent flow is smaller than in laminar flow. These phenomena can be observed experimentally in a laboratory. To this effect, a pilot-scale flow loop simulating a casing eccentered in an annulus was built. The experiment cell itself, made of an outer transparent plastic tube and an inner brass pipe. The inner pipe can be precisely eccentered using two micrometers at the top and bottom. Experiments were performed displacing one fluid by another under two flow regimes for the displacing fluid, turbulent and laminar. Although the phenomena observed appear very similar for the two flow regimes, they do not derive from the same physical nature and should not be confused. The experiment shown here was performed with water as the displacing fluid, pumped at the critical flow rate for turbulent flow, assuming a concentric pipe. However, at this flow rate, if the inner pipe is eccentered, water is flowing only on the large side of the annulus, leaving a channel of mud from top to bottom on the narrow side. This mud channel is extremely stable and cannot be removed by pumping at the same rate for an extended amount of time. As shown on the mud displacement efficiency plot, efficiency is already quite high. However, due to excentration, the angular section left with mud is still sizable, and this is really the parameter to consider for downhole zonal isolation. When increasing the rate, the width of the mud channel decreases as seen on the cross-section schematic, and this is reflected on the efficiency plot. As explained previously with the two parallel pipes analogy, if the displacing fluid flows both in turbulent and laminar flow regimes simultaneously when considered to be alone in the annulus, the mud will only be displaced in the turbulent section. The mud channel eventually disappears when water is in turbulent flow all around the pipe. Mathematical models have been developed by Dh153 to calculate the critical rate for turbulence in an eccentric annulus. That is, the flow rate at which turbulence exists all around the pipe. An excellent agreement was found between the actual rate for full displacement and the calculated critical rate in all our experiments. The second set of experiments was performed with a viscous displacing fluid in laminar flow. Again, at low flow rates, the displacing fluid is flowing only in the wide side of the annulus, leaving a stable channel of mud on the narrow side. This time, this is due to the fact that the wall shear stress is still lower than the mud yield stress on the narrow side, as previously explained with the two parallel pipes analogy. When increasing the flow rate, the wall shear stresses increase in the annulus and the width of the mud channel is reduced. Eventually, the rate reaches a level where the mud yield stress is exceeded by the wall shear stress everywhere, and a full annular displacement is obtained. Starting the experiment at a flow rate such that the wall shear stress on the narrow side exceeds the fluid yield stress allows a full displacement of the mud all around the annulus, but with a difference in velocity between large and narrow sides. Calculations of wall shear stress versus flow rate were performed for this pipe geometry, and a very good agreement was found between theoretical and actual flow rates for full displacement. Experiments have shown that eccentricity is playing a major role on the mud displacement efficiency, and fundamental physics and fluid mechanics can be used to explain why, under certain conditions, a channel of mud is left on the narrow side of the casing. This phenomenon can be observed both in turbulent and laminar flow, but not for the same reason. In laminar flow, the local shear stress must exceed the mud yield stress to ensure complete displacement, whereas in turbulent flow, this condition does not need to be satisfied, but the important factor is the presence of turbulence all around the pipe. When incomplete displacement is obtained in an annulus, an increase in flow rate will eventually allow these criteria to be met and ensure complete mud removal. These experiments and the associated theoretical work have allowed us to improve our understanding of the displacement of a drilling fluid in an eccentric annulus.